Welcome back to Drawing Distributions. In this video, let's explore another conjugate Bayesian model. I'm sure many of you are familiar with the conjugate model for estimating the mean of a normal distribution with known variance. But what about the other way around? It turns out that the inverse gamma distribution is the conjugate prior for the variance in this model. The inverse gamma distribution is the distribution of the reciprocal of a gamma-distributed random variable. Like the gamma distribution, it is a positive continuous distribution with two positive hyperparameters, a shape parameter alpha and a scale parameter beta. To compute the posterior, we need to turn the handle on the Bayesian machinery by multiplying the likelihood by the prior. The likelihood is a product of normal distributions. Let's start by dropping the constant term and moving the product of n 1 over sigma terms outside. The equal sign is replaced with proportionality to reflect this. We now have a product of exponential functions that can be simplified to a single exponential of the sum of the arguments. We can also drop the normalizing constant from the inverse gamma prior distribution. The computation involves matching pairs of terms in the likelihood and the prior. The first term is a multiplication of powers of sigma squared. The second is a multiplication of exponential functions. If we collect these terms together, we get something proportional to an inverse gamma distribution with updated values for its hyperparameters. We can normalize to a density that integrates to 1 by applying known results of the gamma function. The new value for the shape parameter is the prior value plus half the sample size. The new value for the scale parameter is the prior value plus half the sum of the squared deviations from the mean. This is all the information we need to interpret the prior hyperparameters. In this example, it makes sense to consider prior information as prior observations from the same data-generating process. By doing so, the prior value for alpha can be thought of as half the prior sample size, and the prior value for beta as half the sum of squared deviations from the mean, calculated from prior observations. Multiplying by 2 produces a simple and memorable description. 2 alpha is the total sample size, and 2 beta is the total sum of squared deviations from the mean, factoring in data both old and new. Let's look at the Bayesian update of the inverse gamma prior using simulated observations. I sampled 60 observations from a normal distribution with a mean of 1 and a variance of 2.25. 10 of these observations were used to set the prior hyperparameters according to the rule just described. The remaining 50 observations were used to perform the Bayesian update in batches of 10. The section in purple represents the 90% highest density interval. Given the data and the model, this is the narrowest interval that the parameter value has a 90% probability of falling within. The vertical dotted line is the true value of the variance for this simulated data. The prior is consistent with this value, which is ideal. As more data is observed, the posterior uncertainty shrinks, and the distribution begins to settle around this value. That's it for this video. If you are interested in learning more, I would recommend running this computation again, but with a scaled inverse chi-squared distribution in place of the inverse gamma distribution. I hope this was useful. Please like and subscribe if you feel like it, and I'll see you in the next video.